Okay, welcome everybody to my talk on estimating the oceanic kinetic energy cascade from a long track altimetry. I'm Rene Schubert and I'm a postdoc at LOBS in Brest, working currently with mainly Jonathan Gula, who's at UCLA, and this is a collaboration with Oscar Vergara from Toulouse University, who is an expert on satellite data. So today I'd like to convince you that we don't have to wait for SWAT to produce maps at smaller scales of the kinetic energy cascade, so that we can get that also from a long track altimetry. Now, the oceanic kinetic energy cascade, which we all know is the flux of kinetic energy between currents of different scales, it's at the heart of the climate system, as it mediates, besides the cascade of potential energy, the balance between the large-scale forcing by the atmospheric winds and the small-scale dissipation to heat. It controls the strength of all dynamical features, including the subtropical gyre, Gulf Stream, and other large-scale currents, Agulhas leakage, and mesoscale eddies, and thus also the associated transports of momentum, heat, salt nutrients, and oxygens. Finally, it could also be shown that it impacts the state and development of the atmospheric circulation and its response to external forcings. Now, early results by Scott and Wang 2005, who estimated the cascade from Aviso-derived velocities, showed an inverse cascade at scales larger than 75 kilometers, here a wavelength of 150 kilometers, and a forward cascade at smaller scales. Now, in model simulations, for example, Q et al. 2014, they found if they resolve the submesoscales, or at least permit them, the inverse cascade extends to much smaller scales, down to the mixed layer Ross radius of deformation, in particular in spring, which you can see in the Hoffmann plot on the right-hand side. There. Now, if they low-pass filter the data before the flux computations, in a similar way as it is done by Aviso in the interpolation of the long-track data, they end up with results that are very close to the Aviso ones, with this strong forward cascade extending to the larger scales. So, and they could conclude that this forward cascade is an artifact of the low-pass filtering. So we can't trust the Aviso data at the smaller scales, only at the very large one. And Wang et al. 2015 produced, which I think is the only map of the cascade at very large scales. So what is shown here on the left-hand side is their figure, where they show the maximum inverse cascade at the scale where this maximum occurs. And not surprisingly, the cascade is very large in the large-scale current system. Everywhere else, we have very low fluxes where the cascade has already arrested at these scales. Now, if we have a look on the top right figure again, we can see that in the simulations, we find a strong seasonality of the cascade with a spring maximum that shifts slowly within 2 months to the larger scales. And in a study of colleagues and myself from 2020, we could show that this scale kinetic energy flux, which is shown here in the contour lines, is aligned with the kinetic energy anomaly. And there's a study by Storer et al. 2022 from last year where they show that the geostrophic kinetic energy spectrum also shows these anomalies propagating from the smaller scales to the larger scales in both hemispheres with opposite sign. Now, in our study from 2020, we could attribute the process to this cascade, that is the absorption of submesoscale mixed layer vortices by the mesoscales. And so based on this work and a lot of previous work, the theory behind the seasonal cycle is that we have very deep mixed layers in winter, where fronts can pile up very largely, store a lot of available potential energy, that then is converted to kinetic energy by mixed layer instabilities. And a lot of small scale vortices develop that are then absorbed by the mesoscales within 1 to 3 months. And after that, we have a further inverse cascade. Now, indirect indication that this process and the associated cascade occurs in large parts of the ocean is presented by Steinberg et al. 2022, who showed here in the top left panel the month where the available to eddy kinetic energy conversion peaks, which is shown here from Argo data and is usually in winter time. And then they take a long track SSH data and derive the month where the eddy kinetic energy peaks at smaller scales, and then with a very similar month shown in this middle panel. And here you can see the lag between the peak in eddy kinetic energy at the small scales and the larger scales, which is about 1 to 3 months. consistent with the mechanism I described before. However, they could not show the inverse cascade, only indirect indication for it. Now the inverse cascade and the scale kinetic energy flux, also in the forward, has been investigated only regionally. So regional maps have been produced by simulations. And as we also heard yesterday, there are progresses computing the cascade from observations. For example, Bavara et al. 2022 derived the cascade from drifter clouds in the Gulf of Mexico. Q et al. Used also structure functions to estimate the cascade from shipboard measurements along 165 degrees east. And Garabato et al. Used the osmosis mooring in the Northeast Atlantic to estimate the cascade. On the modeling side, I'd like to highlight two studies from last year by Contreras et al. And Srinivasan et al. 2023, where they use Helmholtz decomposition to show that the rotational part of the flow is the one that is responsible for the inverse cascade, which has been shown also in different contexts in other studies. So to summarize, at the moment for scales below 100 kilometers, the near surface kinetic energy cascade and its seasonal cycle could not be investigated for large regions of the ocean and has been investigated only very regional. And here we'd like to close this gap by two steps. First, by computing the cascade from the total and the geostrophic velocity components from a simulation that spans the whole Atlantic, as you can see there on the right-hand side. There we use GGADL1, which is a Croco-Rom simulation with 900-meter grid spacing. And after a couple of years of spin-up, we have 1 year of data that we investigated for the study here. And the second part is then the larger one on estimating the global geostrophic cascade from JSON tree along track SSH with the help of this simulation. So to this first part, only one slide. So shown here are the results for the scale kinetic energy flux on top from total velocity components and on the bottom from geostrophic components. You can see in the time mean at 70 kilometer scales that the strongest fluxes occur in the regions of the large scale near surface current systems. And the middle panel on the right, I show area averages as a function of scale and time. And those are shown here for the region north of 25 degrees north. The one without hedges is shown in the middle, and the one in the open ocean shown on the right-hand side. And there you can see that we have a wintertime and springtime inverse cascade dominating over the forward cascade, and also this shift to larger scales in the simulation. While in summer we have the dominant forward cascade that is stronger at the smaller scales. And as we heard also in the talk by Anne Bendinger and what Ajay et al. Showed in their unpublished paper, is that this forward cascade is much weaker if we don't have tides in the simulation. So this forward cascade is driven by wave-dominated flow. However, if we then go to the geostrophic flow now, this is associated with a problem, namely that if you have SSH gradients that are not dominated by balanced flows, we can't compute geostrophic velocities correct from them. So we can see this problem here in the tropics enormously, and this meridional extent of this band of noisy pattern grows with decreasing scale. Now, north and south of it, we can see that the geostrophic currents can be computed, and we can see that the geostrophic flux is usually inverse everywhere in the time and area mean. And we can also see this maximum here propagating from spring to larger scales in the end of spring with the same amplitude as in the total flux. However, in summer, we can see some problems with the geostrophic flux, where we can see this spurious maximum, which is potentially not physical. Now, to the second part, so we have since decades a long track data that can measure geostrophic kinetic energy levels down to 30 kilometers and below, at least in wintertime. Why do they not have been used to compute the cascade between 30 and 100 kilometers? And the reason is that it's not computable directly. So if we take, for example, the coarse-graining scale kinetic energy flux equation, where U and V are the horizontal velocity components and overlines mark convoluted fields where the small scales are smoothed out. And I write here the Leonard stresses, so these brackets as tau. And if we think about that, we don't have the SSH field as in 2 dimensions, but only in 1. We can compute only the cross-track velocity component and its along-track derivative. So only these 2 terms, this one and that. However, here in our study, we show that one can estimate the 5 times 5 degree average flux by this formula. So we have an estimation coefficient C, which we assume to be constant, and the 5 times 5 degree averaged tau UU and 5 times 5 degree averaged absolute value du dy. So what we do is we compute the 5 times 5 degree average geostrophic flux from P-1, then average it in 5 times 5 degree boxes, cut the simulated SSH from the simulation, and compute the product on the right-hand side. So in the simulation, we have both sides, so the true flux and this product, so we can identify the C. And then we put in here the observational values and can estimate the flux from the observations. To show you that this works, here's the comparison of the time mean flux at 70 and 140 kilometer. And in the simulation from here, they're shown the original values and here the estimated one. And we can see that the horizontal pattern and amplitudes are very close to each other. We have a look on the difference only in very specific region, namely the separation of the Gulf Stream. We found that the estimation does not work. If we have a look on the area averages, we can see that the estimate also reproduces this strong inverse cascade maximum in spring and the shift to larger scales afterwards. And we only have some underestimation at the very small scales in winter and a bit of overestimation in summer. So now we have the C and the proof that the estimation works, and we can put the observational data here and estimate the flux from the long track data. The results are shown here. Time means at 70, 140, and 200 kilometer. We can see at 200 kilometer, the time mean is very close to the Bang et al. 2015 results. So strong fluxes in the large scale currents and arrested cascade in the open ocean. However, at 70 kilometer, we can see that we have also rather strong values of the cascade in the open ocean, consistent with that we have everywhere mixed layer instabilities and the subsequent inverse cascade of the energy to larger scales. And this is the final slide on the results showing the seasonality. So this is FMA anomaly and ASO anomaly, where we can see the springtime enhancement of the cascade at 70 kilometer in both hemispheres. Surprisingly, in the large-scale current system, we found a rather opposite seasonal cycle, which has to be clarified which process is responsible for that. In the open ocean, we can see that the inverse cascade has its maximum in spring, this shift within 2 months to larger scales, consistent with the mechanism I described. So to summarize, with the simulation, we showed that it's possible to estimate the geostrophic cascade at 5 times 5 degree resolution from long track altimetry. And with this, for the first time, we produce maps of the kinetic energy cascade at scales below 100 kilometer. And the inverse cascade peaks in late spring and late winter at scales of 40 kilometer, and its maximum shifts to larger scales in spring, consistent with the absorption of mesoscale eddies after the submesoscale season. And with that, I'd like to conclude, and thanks for your attention and looking forward to questions.